Okay, let's go ahead and apply the formula of washers on this example. So this example says, let R be the region bounded by the curves y is equal to x squared and y is equal to root s. Let S be the solid created by revolving this region around the x-axis. And we're asked to sketch R, S, and a typical washer. Then find the volume of S. Okay, so let's go ahead and start that. So the first thing I want to do is sketch my curves. I'm going to sketch, first of all, the square root function. So the square root function is here. So y is the square root of x. I'll go and add the parabola. Right, so there is y is equal to x squared. And to find the a and the b, well, it's pretty easy. You can probably see or guess what they are. It's 0 and 1. But if we didn't know that, we'd have to set up an equation, right? We would set a system of equations, or set the two equations equal and solve for their points of intersection. And if we did that, we'd square both sides and bring the x over, factor out, and we would see that there are indeed two solutions. X is 0 and x is 1. So there is my a value and there is my b value, and the region R that we're looking for is this region in between the two curves. Okay, so there's our region R. Now, we're asked to revolve this around the x-axis. So let's go and sketch what that would look like. So if we take our same curves here, the square root on top and the parabola on the bottom, and let's just draw the image of what we would get if we rotated these things around, right? So we're getting a solid that looks like this, where the inside here is hollow. It's like a wine glass with very thick walls, right? So the inside is hollow, but there's all sort of this region here is creating thick walls. And when we're going to find the volume, it's not the volume of the hollow part. No, the volume is going to be the volume of the walls. So if we're thinking about a wine glass, it's the amount of plastic or glass that would be in the walls, not how much wine the cup could contain. So the volume is going to be the amount of material in the walls. So the amount of material in the walls. All right, so we're asked to sketch a typical washer. So a typical washer would look something like this. But it's a washer, and so it is hollow. It's hollow, and so there we are. Let's get a little bit of color in here. So there's a typical washer. And we want to use the sort of the memory aid version of the formula that the volume is going to be the integral from a to b of pi times the big radius squared minus the little radius squared dx. So we've already figured out that our a is 0, right? We had that up here. Our b is 1. So what is the big radius? The big radius goes from the center to the outside, and so our big radius R is the curve in red, and the curve in red was the square root function. Our inner radius, our small radius, goes from the center to the inside hollow part, and so our small radius R is the curve in blue, and the curve in blue is x squared. So if we go and plug all of this into the volume, we're getting the integral from 0 to 1 of pi times big radius is the square root squared minus little radius is x squared squared dx, and that's the hard part. After that, then we just need to evaluate. So if we go ahead and do that, we're going to do integral from 0 to 1 of pi times, if I square the square root, I get x, minus x squared squared is x to the 4th dx. I will bring out the pi. Using FDC2, I need antiderivatives here. So 1/2 x squared minus 1/5 x to the 5th. Those are going to be evaluated from 0 to 1. And that is going to give me pi times 1/2 times 1 squared minus 1/5 times 1 to the 5th minus 0 minus 0. And so this is pi times 1/2 minus 1/5. Let's put these both on 10. So 5 on 10 minus 2 on 10, which is going to give me 3 pi on 10 cubic units.